As a child, I was fascinated by the patterns made by kaleidoscope. And what I found particularly absorbing was the way the pattern kept on changing. Perhaps you did too. Today, however, I'm more concerned with the nature of the pattern itself.
How is it formed? Well, the picture you're seeing is actually coming from a scaled-up replica of my kaleidoscope. This is where the coloured shapes come from, just bits of coloured plastic. But there's no pattern there. It's just a jumble. It's all done by mirrors. The pattern you were seeing was generated by multiple reflections in the three mirrors, reflections of a random collection of bits of coloured plastic. To see just what the mirrors are doing, let's replace the moving jumble of plastic fragments by something fixed, some motif we can easily recognize.
Let's see what that has to do with the wallpaper patterns you've been looking at in the unit. We've reproduced the kaleidoscope pattern on paper so I can study it more closely. It obviously is a wallpaper pattern, even though it's been generated as multiple reflections in a kaleidoscope. That is, it has translational symmetries in two independent directions. Horizontally and at 60 degrees to the horizontal. In fact, it also has rotational symmetries of order 3. Here's a copy on which we've superimposed all the three centres. On one of the centres, we've put 3 rays at 120-degree angles, and the same on an overlay. So that I can demonstrate the 1/3 rotational symmetry. One third, another third, and back to the start. Before we leave this pattern, let's see how these rotations and translations arise. Remember, the pattern was originally formed just using mirrors, so we only had reflections. How can these reflections produce a pattern with rotations of order 3 and even translations? Here's a version of the pattern on which we've superimposed the triangle of mirrors and the reflections of the mirrors. And I can demonstrate, with this triangular piece of perspex, how multiple reflections can generate 3 centres and even translations. The first thing I want to establish before using the triangle is that all these lines are axes of reflective symmetry, even though only these 3 line segments represent real mirrors. Let's look at this line and concentrate on this segment of it. It's the reflection of the vertical mirror in the bottom mirror. And when we reflect the vertical mirror, we also reflect the image in it. So this image is reflected to here. But look, this means that the reflection of the mirror acts like a mirror. This triangle is just a reflection of this one. And the same is true of all the line segments. They all act as mirrors. So all these lines are axes of reflective symmetry. So how are these reflections going to get us the rotations and translations. Let's start off by looking at a rotation. To get a rotation of a third, I can go about this centre round to there. But I want to achieve that using reflections only. Well, I can do that by reflecting in this line, like that, and then in this line, like that. So that's given me the 1/3 rotation. Well, what about the translations? I'm now back where I started, and I want to see if I can get from there to the translated position here, using reflections only. Well, I'll start off with a 1/3 rotation, which I know I can achieve using 2 reflections. And now I'm going to rotate through an angle of -1/3. About this point here, I can get to the translated position I want. And I can achieve that again with 2 reflections. Once, twice. So using reflections only, I've moved from here to the translated positions there.
So now you know how a kaleidoscope produces a wallpaper pattern. Now every wallpaper pattern is based on an underlying lattice. We can show you the lattice on which the kaleidoscope patterns are based. All we need do is to put a coloured dot at the top of the generating triangle. The pattern formed by the dots is the underlying lattice. In this case, it's the type we call a hexagonal lattice. Putting aside for the moment these hexagons surrounding the lattice points, let's now join the lattice points to form a parallelogram grid. Then we can see quite clearly the relationship between the lattice and the wallpaper pattern. Within each parallelogram of the grid, there is precisely the same motif. We'll come back to the kaleidoscope again later, when we go into more detail about the relationship between wallpaper patterns and lattices. So before proceeding further, we first need to know more about lattices.
Roy showed you a hexagonal lattice, but that isn't the only kind of lattice you'll meet. There are, in fact, 5 kinds of lattice: parallelogram, rectangular, square, rhombic, and hexagonal. Any lattice is defined by choosing the origin as one of the lattice points and then choosing 2 basis vectors, A and B. The origin, together with the lattice points at the ends of the vectors A, B, and A plus B, then form the vertices of what we call the basic parallelogram. And the other lattice points are defined as MA plus NB for every pair of integers m and n. For example, here's the lattice point A plus 3b. And here's minus A minus B. What sort of symmetries do we have? We can be sure of some types of symmetries, whatever type of lattice we're looking at. By the very definition of a lattice, all lattices have translational symmetries in the direction of the 2 basis vectors. In the direction of A, and B. Now, what about rotational symmetries? Well, every parallelogram has a centre of rotational symmetry of order 2 about its centre. And so every lattice has rotations of order 2 about the centre of each translated image of the basic parallelogram. Here we are. Take this point, for example. If I rotate about here by 180 degrees, then the pattern coincides. So far, what I've said is true of all types of lattice. We'll have translational symmetries in the direction of the basis vectors and rotational symmetries of order 2 about the centre of each parallelogram. Now let's look at each type of lattice in turn, starting with the one which has the fewest symmetries of all. If there are no indirect symmetries, then we have what is called simply a parallelogram lattice. We'll see that this means the basis vectors can't have the same lengths, and the angle between them cannot be a right angle. Although a parallelogram lattice has no axes of reflection and no rotations of order greater than 2, it does have further 2 centres. See if you can tell where these will be. We'll indicate the symmetries only on the basic parallelogram. There are further 2 centres at the lattice points and also at the points midway between the lattice points. Let me demonstrate one or two. First, rotation about a vertex. And about this midpoint. And that's it. The only symmetries we have are the translations parallel to the basis vectors and their combinations, and the rotations of order 2 about lattice points and about points midway between them, including the centres of the parallelograms. We can confirm there are no reflections the reflected pattern can't possibly coincide. If I match a side, the angles don't match, and if I match the angle, the sides don't match.
That's the simplest type of lattice, and we've reproduced it here in the form of a trellis, so that we can distort it to get the next type of lattice. And as we reach an angle of 90 degrees between the basis vectors, the basic parallelogram becomes a rectangle, which gives additional symmetries. For example, reflection in the horizontal line parallel to the basis vector A. There. The lattice points of the reflected version coincide precisely with the pattern of the original lattice. And the same is true about any vertical line parallel to the b-axis.
Let's build up a record of all the symmetries we find, and for simplicity, we'll mark up just the basic parallelogram, which in this case is a rectangle. We denote axes of reflection as solid lines extending through the lattice points. Is that all? Can you think of any other axes of reflection? There are axes of reflection midway between those we've already observed. Let me demonstrate one. For example, reflection in the horizontal line through the middle of the parallelogram. I've marked the axis on the overlay. Now, reflect in this axis. How about centres of rotation? The rectangular pattern might tempt you to look for rotations of order 4. But if we try rotating through only a quarter of a turn, the long edge would end up vertical, so we'd be trying to match it with the short edge. So centres of order 4 are not possible, but we still have a parallelogram. It is admittedly a special one, where the angle is a right angle, but it must still retain all the parallelogram 2 centres. That is, at each lattice point and at the points midway between them. So all we've gained by making the angle a right angle are the indirect symmetries, the reflections. And that's dealt with the parallelogram and rectangular lattices, where the basis vectors are of different lengths. For the remaining lattices, we drop this restriction. If we squash the rectangular lattice until the basis vectors become equal, what we get is a square lattice. Have we introduced any new symmetries? Well, we now have centres of rotation of order 4. Fairly obviously, each square has a fourfold rotation about its centre. And it's a fourfold rotation of the entire lattice. What about the other points that used to be only 2 centres? Have any more been upgraded to 4 centres? Yes, there's a 4 centre at each lattice point. Let me demonstrate one of them. What about indirect symmetries? Well, we kept the reflection lines marked on the diagram when we squashed the rectangular lattice into a square one, because of course the square lattice retains all the indirect symmetries of the rectangular lattice. And there are more. A square is symmetric about each of its diagonals, so the square lattice also has axes of reflection diagonally through the lattice points. Let me show you that. And the same is true for the other diagonal. Any more axes of reflection? Well, we've looked at all the lines joining centres of rotation of order 4. What about lines joining centres of rotation of order 2? It turns out that these are not axes of reflection. Here's what happens. The lattice points don't line up. They're halfway between the originals. But we can make them line up by performing a translation in a direction parallel to the attempted axis of reflection. Notice that this cannot be achieved by combining any of our translational symmetries with any of the reflections we've found, because the translation required is through only half the diagonal distance between lattice points. But we've seen that there is a symmetry of the lattice which is achieved by reflection in this new axis, followed by the half translation. This is called a glide reflection, and it's the other kind of indirect symmetry. We'll use dotted lines from now on to indicate glide reflections. This picture records all the symmetries of the square lattice. There are 2 more lattice types to look at: rhombic and hexagonal. Like the square lattice, these last 2 have basis vectors of equal length.
We can derive both types by distorting a square trellis. And we're going to swivel the rods so as to change the angle between the basis vectors, all the time keeping their length equal. We now have a rhombic lattice, and we appear to have lost the reflective symmetries as soon as we moved away from 90 degrees. Or did we? If we rotate the trellis until the diagonals are horizontal and vertical, then it's clear that there are still reflections in the diagonals.
Let's record those on the basic parallelogram. There are no reflections in directions parallel to the basis vectors, but there are in vertical and horizontal axes. As for rotations, we have now lost all the centres of rotation of order 4. But, as for any lattice, there are 2 centres at all the lattice points and midway between them. There are also glide reflections in axes midway between the axes of reflection. Those glide reflections are easier to see if we add the lines of the trellis. On the overlay, we've drawn just a part of the grid, one column of rhombuses. On the basic pattern, notice that adjacent to this central column is another column of rhombuses, but they're offset, half a diagonal to the right and half a diagonal upwards. The glide reflection I'll demonstrate maps this central column to the offset column. Reflection in the dotted line offsets the central column half a diagonal to the right. And now translate half a diagonal upwards. Finally, the hexagonal lattice.
Let's rotate the trellis back to its original orientation with one of the basis vectors horizontal. And now we're going to swivel the rod still further. Notice, the reason there's no reflection in any horizontal axis is that the lattice points above and below any horizontal grid line don't line up vertically. So let's swivel this further until they do so. And if you check, you'll find that we must now have the angle between the basis vectors reduced to 60 degrees. And then we have the hexagonal lattice, which you met at the beginning of the program.
Perhaps you'd like to mark up the basic parallelogram yourself, showing all the centres of rotation with the orders of each, and all the axes of reflection and of glide reflection. This diagram is reproduced in your video notes. There's a very large number of symmetries. The axes of reflection include the four sides and the two diagonals, and also the perpendicular bisectors of the sides. For the rotations, every lattice point where 6 axes cross is a 6 centre. Then on the long diagonal, there are 2 rotational centres of order 3, at the points where 3 axes cross. And there are centres of order 2 wherever 2 axes cross, that is, midway between lattice points. Finally, the glide reflections. Just as for the rhombus, there are glide reflections in axes passing through the centres of order 2 in directions parallel to the axes of reflection. There are now 6 directions instead of only 2. Let me demonstrate a few of these. A 3 centre. That's a third, 2/3, and a full rotation. A reflection in a side. And a glide reflection in an axis through the centre.
It's time we began to think about wallpaper patterns. Let's make up one of our own. All we need do is to take a basic parallelogram, put some sort of motif in it, anything will do, and then cover the wall or the entire plane with exact copies of the basic parallelogram. If you have chosen a nice enough motif, the result may be a very attractive wallpaper, but it's unlikely to be very interesting mathematically, because in general, it will have no symmetries other than the translations, which any wallpaper pattern must have. In contrast, we got a much more interesting pattern using the kaleidoscope. So if we haven't got a kaleidoscope, how can we manage to get more interesting patterns? What we need to do is somehow to introduce more symmetry. Our first attempt at constructing a wallpaper pattern produced only the simplest type of pattern, called P1 in international notation. The letter P refers to the primitive cell, which is an alternative name used for the basic parallelogram. And the following digit records the highest order of rotational symmetry present. So all we have is the trivial rotational symmetry of order 1, no rotation at all. That seems a great pity, because even the simplest lattice has other symmetries. Suppose we start with a simple parallelogram lattice. How can we be sure to retain the rotational symmetries of order 2? Think about it. The diagram is reproduced in your video notes. The answer is you have to make sure that whatever is put in the basic parallelogram has itself the desired rotational symmetry. One half of the parallelogram must look exactly the same as the other half. You can split the parallelogram into two equal halves in any way you like. The triangle formed by the basis vectors will do very well. And now, if you put anything in this triangle and then rotate it through 180 degrees about the center of the parallelogram, you will get the other half of the basic parallelogram. And then, when the plane is covered with copies of the basic parallelogram, you will have a wallpaper pattern with all the symmetries of the parallelogram lattice. That is, the 2 center, at the center of each parallelogram, is assured by the fact that we put a pattern into it that has the required symmetry. Also, the other centers of order 2 exist for the same reason. For example, rotating about this midpoint maps the bottom half of the basic parallelogram into the top half of the adjacent parallelogram. Such a pattern is referred to as being of type P2, because 2 is now the highest order of rotational symmetry. The triangle upon which the whole pattern is based is called the generating region. It is a region of the smallest area, such that its images under all the symmetries of the pattern cover the entire plane. The generating region is not unique. Other regions can be used to generate the pattern. Can you think of one for this pattern? Any way of splitting the basic parallelogram into two identical halves will do, because then the two halves will map into each other under 180-degree rotation about the center. For instance, you could split the parallelogram by the long diagonal, giving a different triangular region, or by a line parallel to either of the basis vectors, which means the generating region is itself a parallelogram. It's interesting to consider suitable generating regions for the other 4 lattice types, where by suitable we mean a region which will generate a wallpaper pattern retaining all the symmetries of the underlying lattice. Firstly then, let's take a look at the rectangular lattice. Its type is denoted as P2MM, the 3rd and 4th characters referring to mirror reflections in 2 directions. In order to generate a wallpaper pattern of this same type, it turns out that we may take as generating region a rectangle 1/4 the size of the basic parallelogram. Let's see how that works. Whatever pattern we put in here, we can apply the 2 reflections to it in order to fill the parallelogram. Alternatively, we could use just one of the reflections, followed by the rotation of order 2. And now the pattern can be translated to cover the whole plane. It's important to remember that we've made sure our wallpaper pattern retains all the symmetries of the P2MM lattice. There are patterns based on this lattice, but with a different generating region, which lose some of the symmetries, and we'll see some later. For the moment, let's continue with patterns that do preserve all the symmetries of the lattice. And we'll move on to the square lattice. The type of a square lattice is denoted P4MM, because now there's a rotation of order 4 about the center. To generate a wallpaper pattern with the extra symmetry, we must take a generating region only 1/8 the size of the square. A triangle will do. To fill the square, we can apply one reflection and successive rotations of order 4. Although, again, we could achieve this just with reflections. Whichever method we use to fill the square, we now use translations to cover the plane. Now for patterns based on the rhombic lattice. This lattice is sometimes known as a centered rectangular lattice, and that's because each vertex is at the center of a rectangle of 4 neighboring vertices. And because of this way of looking at it, its type is denoted by C2MM, the C standing for centered. The 2 tells us that there are no rotation centers of order greater than 2. And the 2 M's now refer to reflections in axes parallel to the diagonals of the rhombus. The diagonals of the rhombus divide it into 4 right-angled triangles, one of which we take as the generating region. Finally, the hexagonal lattice. It has rotations of order 6, and it has reflections in axes perpendicular to the basis vectors and also parallel to them. So its type is denoted by P6MM. Because of all the reflective symmetries, we need a generating region 1/12 the size of the basic parallelogram in order to ensure that we retain all the symmetries. Incidentally, the generating region could be any of the little triangles that our original one was mapped to. For example, it could be at the bottom left. In either case, once the parallelogram is filled, we translate it as before to cover the plane. If we study this pattern, the first thing that strikes you is a number of distinctive motifs. Looking at this motif, we can see a pair of reflective shapes rotated around 3 times. And the same is true at this 3 center. But if you look at this lattice point, we can still see a pair of reflected shapes, but now they're rotated around 6 times. Actually, we've already seen a wallpaper pattern based on the hexagonal lattice, the kaleidoscope pattern. It doesn't have as much symmetry as P6MM. It's called P3M1, which tells us that the highest order of rotation is 3, and the M denotes that there are reflections perpendicular to the basis vectors, and the 1 that there's no indirect symmetry in the short diagonal. In the unit, you will see why the symbol 1 is used here. To appreciate the differences in detail, let's overlay a marked up basic parallelogram for P6MM and also for P3M1. And now you can see that if we compare it to P6MM, we've lost all these indirect symmetries in lines parallel to the basis vectors, or indeed to the short diagonal. We've also downgraded the 6 centers at lattice points to 3 centers. And that's equivalent to the fact that there are now only 3 axes passing through the lattice points instead of 6. And we've lost all of these 2 centers. Now, how does this reduction in symmetry relate to the way in which we generated the 2 patterns? For P6MM, we used this little triangle as a generating region and mapped it into the rest of the parallelogram using the P6MM symmetries. For P3M1, we used this double size generating region and we mapped it using the reflections in the kaleidoscope mirrors. But, and this is the important point, the motif that we placed in here was asymmetrical. Look what happens in the kaleidoscope if the motif we use is symmetrical. Lo and behold, we get P6MM. Let's look closely at the original symmetries to see why the symmetrical motif in the generating region results in all the extra symmetries. By putting a symmetrical pattern in here, what we did was to introduce another reflection in the direction parallel to the short diagonal, just like the one that P6MM has. And as soon as you introduce that, you also get the reflections of this reflection. So altogether, you land up with 6 directions in which you have reflections instead of only 3. And where 6 axes meet, this gives you a center of order 6. Now, aesthetically, it's a matter of personal choice which pattern you prefer. P6MM has extra features to interest you visually. That's these reflections and a 6 center. On the other hand, it has only one type of 3 center, because this 3 center is just a reflection of this one. That's to say, these 2 3 centers are images of each other under one of the symmetries. Whereas, for P3M1, the 2 are distinct 3 centers.
So far, we've seen 7 types of wallpaper pattern. 2 of them were based on the parallelogram lattice. Then we saw one based on the rectangular lattice, another based on the square lattice, another based on the rhombic lattice, and finally, 2 based on the hexagonal lattice, one retaining all the symmetries and the kaleidoscope pattern with some symmetries missing. In the unit, you'll find a further 10 types, making 17 in all. We've seen an example having each of the orders of rotation. In fact, we've seen examples of 3 of the types with rotation of order 2. We're not going to look at all 17 types, but let's have a look at all 3 of the remaining patterns with rotations order 3 and 6, P3, P31M, and P6. Now, any pattern with rotation order 3 or 6 must be based on the hexagonal lattice. What distinguishes these patterns is the particular symmetries for each acting on a suitable generating region. We've seen that a triangle of 1/12 the area of the basic parallelogram is sufficient to generate the pattern P6MM, whereas we needed a triangle of 1/6 the area to generate P3M1. What about the pattern P31M? We can use this triangle, also a 1/6 of the area, to generate P31M. We've shown it superimposed on the basic parallelogram, marked up with all the symmetries. So how does this differ from P3M1? Well, we now have a 1 instead of an M in the 3rd position. This indicates that we no longer have an axis of reflection perpendicular to the left-hand side of the basic parallelogram. For example, this axis is not an axis of reflection, as it was for the kaleidoscope pattern. The M in the fourth position indicates that there are axes of reflection in other directions. In this case, there are axes parallel to both sides of the parallelogram and to the short diagonal. Let's choose a motif. In order to generate this pattern, we can't use just reflections, as we did for P3M1, the kaleidoscope pattern, because in this case, two of the sides of the generating triangle are not axes of reflective symmetry. So we're forced to use rotations to fill the basic parallelogram. And we complete the job with a final reflection in the short diagonal. And now we can use translations to fill the plane. Let's study the pattern. Comparing this with P3M1, the same 3 points are centres of rotation of order 3, but this time the two interior centres are just reflections of each other, just as in P6MM, rather than being distinctively different as in P3M1. Also, the interior 3 centres do not lie on axes of reflection, so the shapes near them don't appear as pairs of mirror images, as in P3M1. And now, let's see two patterns based on the hexagonal lattice, which have no indirect symmetries at all. P6 has centres of rotation of order 6 at the lattice points and of order 3 and 2 at the same points as P6MM, but no indirect symmetries. A suitable generating region is this one. Successive rotations of order 3 will fill half the parallelogram. Finally, a rotation of this half about the centre of the parallelogram by 180 degrees fills the parallelogram. We then cover the plane as before. Let's compare P6 with some of our previous patterns. Rotationally, it looks like P6MM. The only difference is that in P6MM, motif elements appear as pairs of mirror images, whereas in P6, the elements appear as singletons. If we compare it with P3-1M, here, the top right is a reflection of the bottom left, whereas in P6, the top right is a rotation of the bottom left. The final pattern, based on the hexagonal lattice, again has no indirect symmetries. Its type is P3. The highest order of rotation is 3. The generating region this time takes up 1/3 of the area of the basic parallelogram. We put a motif into it as before, but in this case, when we try to fill the parallelogram with images of the generating region, parts of the images will fall outside the parallelogram. For example, rotating 1/3 of a turn about the left-hand interior 3 centre gets us this picture, and rotating again brings us here. Then doing the same about the other interior 3 centre, we end up with this picture. We can still generate the whole pattern by translating just the parallelogram. The pattern that P3 has most in common with is P3M1. Both have 3 distinctively different centres of order 3. The difference is that each centre in P3M1 lies on 3 axes of reflection, so you get pairs of mirror images rotated by 1/3, whereas for P3 the shapes appear as singletons instead of pairs. So that's a total of 5 different types we've seen based on the hexagonal lattice. See if we can put what we've learned about their features into practice.
Take a look at this. You may or may not like the pattern, but have you seen anything similar to it before? Well, it may not seem so, but this pattern is equivalent to the kaleidoscope pattern that we saw earlier. It's also type P3M1. Now, as in this pattern, our new one has 3 distinct 3 centres, which don't map to one another under any of the symmetries. And there are 3 axes of reflection through each of the centres, and in the same 3 directions. Now, I find it useful to imagine a tiling like this for the P3M1 pattern. It's a tiling with 3 distinct shapes, each with rotational symmetry of order 3, and each with 3 axes through them. If I superimpose it on the marked up parallelogram for the P3M1 pattern, then you can see just where the lattice points are. It's another wallpaper pattern, of course. It's also of type P3M1, the archetypal P3M1, you might say. And you may find it useful to compare mentally an image like this one with any pattern which you're thinking might be P3M1. What about this pattern? Seen anything like it recently? Well, it has centres of order 6, and it has reflections. So its type is P6MM, like the pattern you saw earlier. Once again, there is a simple tiling pattern that I find useful to help me visualize the type P6MM. This is actually one of the Archimedean tilings that you met in the first unit. Now, it has hexagons around each of the centres of order 6 and triangles around centres of order 3, which are reflections of each other in pairs. And it has centres of order 2 at the vertices of the triangles. Now, you can see all this, all these centres, when I superimpose it on the marked up parallelogram, which also, of course, shows the axes of reflection through the centres and all the glide reflections. Well, you can check all this for yourself. It's in the video notes. Now, what I've just been doing is looking at equivalent patterns and checking that they are equivalent, that they are of the same symmetry type. But if we want to identify patterns, we'll need to focus our attention on what's different between the 17 different types. If you are presented with an arbitrary pattern, there is a systematic algorithm in the text of the unit for identifying which of the 17 different types you've got. I won't go through the details of the algorithm now, but let's see the kinds of things you'll be looking for.
The basic idea is to check what kinds of symmetries are present. What's the highest order of rotational symmetry? Are there any reflections? And if so, in what directions of the axes? Then there's the location of the centres of rotation relative to the axes. Also, for each order of rotation, how many distinctively different centres are there? That is, centres which don't map to each other under the symmetries. Finally, are there glide reflections? Some of these properties are helpful for determining some patterns, and others are helpful for other patterns. But the property that's always helpful is the highest order of rotation. Once we know the highest order of rotation, we've greatly narrowed down the possibilities. To end the programme, I'm going to look at a few patterns and try to identify them. What about this one? The first thing to look for is the highest order of rotation, which is 4. There's a 4 centre at the centre of each of the flower motifs. So now, consult the table. There are only 3 patterns with rotations of order 4. The first, P4, has no indirect symmetries. P4GM has reflections in diagonals and only glide reflections in directions perpendicular to the basis vectors. P4MM has reflections in 4 directions, as we've seen. So let's see. Does this have any indirect symmetries at all? If so, it's not P4. Yes, there is an indirect symmetry, but to make this superimpose, I have to slide it horizontally. So in fact, I have P4GM rather than P4MM. The 2 axes of reflection are in the diagonal directions. What about this pattern? Again, the highest order of rotation is 4. This time, though, there are lots of reflections. In fact, there are reflections in 4 directions, vertical and horizontal, and in the 2 45-degree diagonals. So this is of type P4MM. What about this? Again, there are centres of order 4, but the motif has a clockwise nature throughout, so there can't be any indirect symmetries. Hence, this is of type P4. Finally, what about this pattern? Again, it has a squarish feel to it, but when you look carefully, it has no centres of order 4. In fact, it's just a squashed version of a pattern you saw earlier, the pattern P2MM, based on the rectangular lattice. So you have to be careful. This pattern, although squarish, is actually P2MM. The point is that the square is a special kind of rectangle, so any pattern type based on the rectangle can also occur with a square as its underlying lattice. In fact, the square is also a special kind of parallelogram and a special kind of rhombus, so all pattern types based on these lattices can also have a square underlying lattice.